Hello. Every digital systems course inevitably starts with numeric bases and the conversion between one base and the other. That is because computers use binary numbers, as you may or may not know, and we as humans use base 10 or decimal base. Now, the base is usually marked with the letter R for radix, and the principle is fairly simple. You start with the digit 0 and you go up with the numbers as you count them. The last digit you reach is the number of the base minus 1. So if we use base 10, the largest digit we have is 9. If we use base 2, the largest digit is 1. If we use base 8, the largest digit is 7. And same with 16, the largest digit is 15, but we'll reach it soon. Now you keep counting one by one until you reach the largest digit, and when you add 1 to that, the digit resets to 0, and you add 1 to the next digit over. You're fairly used to it. When you do 9 plus 1, you get 10, which is 1 and 0. And not surprisingly, 1 and 0 is also the base you use, no matter what base you use. Now, we know decimal is simple for us, because we're used to it. It's time to learn about binary. Binary uses, again, it starts with a 0, and you count up to r minus 1, which is 1. 2 minus 1 is 1. So you have only two digits, 0 and 1. And when you add 1 to 1, you get 1, 0. And when you add 1 more to that, you get 1, 1. Very similar to 11. But when you add 1 to that, the 1 resets, it adds 1 to the next digit also resets, and you get 1, 0, 0. We will see it a bit later. Base 8 counts up to 7 and then resets, and hexadecimal base is base 16. What is special about base 16 that it's worth mentioning? Well, it's very similar to the decimal base, which makes it easier for us humans to read and get a general understanding of the number just from seeing it. The other characteristic it has is that 16 is a power of 2, and conversions between bases that are powers of each other are fairly simple, and we will see it a bit later. Now, because 16 has more digits than we use in base 10, we count normally up to 9, but after that we need 6 more digits, which we don't have. So people decided to use the letters A, B, C, D, E, F instead. So A is equal to 10, the decimal 10, B is 11, C is 12, D is 13, E is 14, and F is 15. And they each can go in whatever digit you use. It doesn't matter, they are just numbers. Now, when you write down a number, no matter what base you use, each digit is worth the base to the power of the placement location of the digit. So the first digit left of the what we're used to know as the decimal point, but because this is not necessarily decimal, we call it a radix point. So left of the point is the singles, the ones. if you're writing a decimal number, you'll have here the ones, the tens, the hundreds, the thousands. The same can be said about every other base. If it's binary, it will be 1s, 2s, 4s, and 8s, and 16s, and 32s, and so on. And the same can be said about after the point. It will be fractions. That would be half, fourth, eighth, 16th, and everything after that. That is in comparison to the decimal, which would be 1/10, 1/100th, and 1,000th, and everything after that. And that applies to the other bases as well. Now, we want to convert numbers from one base to the other, for our use and for other systems' use. We do that because computers don't know decimal very well, and we need to talk to them and they need to talk to us. So what we do is we assign the value of each digit, like I just said. And let's see an example. In binary, here I just wrote some numbers. 1, 1, 0, 1, 0. You don't know what it means. I don't know what it means. You don't know. All we know is this is a number in base 2, which is usually marked as this. In parentheses, it shows the... And all we do is that we multiply the digit by the value of that same digit, depending on the base, of course. So if we're using base 2, r to the power of 0 would be 2 to the power of 0, which is 1. And 2 to the power of 1 is 2, to the power of 2 is 4, 2 to the power of 3 is 8, and 2 to the power of 4 is 16. And all we do is that we multiply the digit by its value, and we add all of those products. So we have 1 times 16, it's over here. 1 times 8, 0 times 4, 1 times 2, and 0 times 1. That adds up to 16 plus 8 plus 2, which is 26. And we know the size of the number itself. You can say we have 26 cupcakes, and that's what we mean. So once you know the size of the number, if you would like to call it like that, you can just write it down in base 10, because you know base 10. Now another example would be with hexadecimal. Here's a random number, 1, 3, 8, 13, 5. The D is worth 13. And what we do is the same thing. We take the base, which is 16 in this case, we take its powers, and we say this is the value of each digit. So we have 1 times 16 to the power of 4, 3 times 6 to the power of 3, 8 times 16 to the power of 2, D, which is 13, times 6 to the power of 1, plus 5 times 1. And we just put this calculation into the calculator, and we get the following number, which is 80,085. And we can write it down in base 10 because, again, we know what it means in base 10. And that's how you switch every base to base 10. You just sum up the values of each digit, and you get a result. Now if you have a fraction, like point something something something, just multiply the value by the negative power of the same base, as we saw in the first slide. Now, say you have a number in base 10 and you want to change it to another base. So here we have the number 26, which we saw earlier in base 10, and we want to know what it is in base 2. What we do is that we take the number and we start dividing it by the base itself, the base we wish to reach. So 26 divided by 2 is 13 with a remainder of 0. We remember the 0, the remainders, because they are important. And then we take the result, 13, and we divide it again by 2. We get 6 and a remainder of 1. Then we take the 6 and we divide it by 2, we get 3 and a remainder of 0. We take 3, we divide it by 2, we get 1 with a remainder of 1. We take 1 divided by 2, we get a 0 with a remainder of 1. And we're done because we reach 0. What we now do is that we take the remainders from last to first. So we have 1, 1, 0, 1, 0. That's a number in binary. And if you go back in the video, you'll see that it's the same number, 1, 1, 0, 1, 0. Here's an example in hexadecimal. It's the same number we got earlier, 80,085, and we want to switch it to base 16. We do it exactly the same way. We take the number and we divide it by 16. If you don't remember how to do long division, all you do is that you take the number and you see if you can get the divisor. You get 16 in 8. You say no, so you try 16 in 80 and you say yes, 80 is larger than 16. 16 gets into 80 5 times. So you do 5 times 16 and you get again 80. You subtract one from the other, you get 0. You take the 0 down, you ask does 16 get into 0? You say no, so you put a 0. You take the 8 down, does it get inside? No. So you put another 0, then you take down the 5 and you say, oh yeah, it gets in 5 times. So you write 5, multiply it by 16, you get 85 minus 80, and you get the remainder of 5. You take the result, 5005, divided by 16, you do the division, and you get 312 with a remainder of 13. You take 312 divided by 16, you get 19 with a remainder of 8. Take 19 divided by 16, you get 1 with a remainder of 3. Take 1 divided by 16, you get 0 with a remainder of 1, and you're done. Now you take the remainders from last to first, and you get 1, 3, 8, 13, and 5. 13 is D, so you get 1, 3, 8, D, 5 in base 16. It's that simple. You can do it with every base conversion you want, from decimal to anything else. If you want to go with fractions, if you have a decimal fraction, you do about the same thing but with multiplications. And instead of remainders, you take the whole numbers and you use them to describe the following digits. But I won't get into that. Now, the reason I said that hexadecimal is important is because hexadecimal is 16 and 16 is 2 to the power of 4. And that means that conversions between binary and hexadecimal are very simple, very straightforward, very dumb. And you do that because it's the power of 4, you take 4 binary digits and you just convert them to one hexadecimal digit. If you went with the octal base, the base 8, 8 as you know is 2 to the power of 3, and you do about the same but with 3 digits instead. And all you do is that you take a binary number, any binary number, I wrote down this long number, 1 0 0 1 1 1 0 0 0 1 1 0 1 0 1 0 1 base 2, and you go from the radix point, like the rightmost point, and you start cutting groups of 4, and you mark it down, and you count another 4 and you mark it down, count 4, count 4. When you reach the leftmost position, you need to fill it up to a group of 4. And as you know from like first grade, every positive number you can just add zeros to the left of it and it won't change its value. So you fill up zeros to your heart's content until you have your appropriate group. So then what you do is that you just look at this chart, which counts numbers in binary, and it counts the same numbers in hexadecimal. So here you have 4 zeros, which is the same as 1 0. You have 1 with 3 excess zeros. Then you add 1 to that, you get 1 0, which is 2. You add 1 to that, you get 1 1. 1 to that, you have 1 0 0, talked about it earlier, and you just keep going with it. Okay, so what you do is that you take your groups and you look at the chart and you match each group with its appropriate hexadecimal value. So here we have 0 1 0 1, we look over here, 0 1 0 1 is 5, we just copy down the 5. Then you have 1 1 0 1, you look over here, 1 1 0 1 is D, you copy the D. 1 0 0 0 is 8, you write down 8, 0 0 1 1 is 3, write down 3, and 0 0 0 1 is 1, you write down the 1, and you're done. You have the number in base 16. Now this goes the other way as well. You get the number in hexadecimal, you just convert each digit to 4 binary digits, as we did earlier, but the other way around. So 5 turns into 0 1 0 1, D turns into 1 1 0 1, and we do it exactly the same. And when you take the 1, you get 0 0 0 1. You know that the leftmost zeros are pointless, so you can delete them, and you get a number in binary. It's fairly simple. Again, it's dumb. You don't need to put a lot of thinking power into it. Okay, negative numbers. Computers and various systems don't have the sign, the capability of using a plus or a minus. They don't know it. All they know is numbers and more numbers. So the people have made a few conventions of how to denote positive and negative numbers. In all of those conventions that I know, which are 3, positive numbers are denoted with a 0 in their leftmost digit. And negative numbers are denoted with r-1, where r is our base, our radix, and r-1 is the largest digit in each base. So if we're talking base 10, it would be 9. If we're talking base 2, it would be 1. And you know that if you look at a number which you are told is signed to some degree, you can just look at its leftmost digit and you can tell immediately whether it's positive or negative by 0 or r-1. And here are the methods. Sine and magnitude. Sine and magnitude is the way we use numbers daily. We get the number 2020, and as I said, you put a 0 on the left side to denote it's a positive 2020. If you want to say negative 2020, just put a 9 on the left. The number itself remains exactly the same. It is unchanged between the positive and negative, because it's a sine and magnitude. Here's an example of taking a signed number in decimal and changed it to binary. So plus 7 is 0, denoting the positive, and 111 is 7 in binary. If you want to say negative 7, you get 1 and 111. So this is positive 7, this is negative 7 in base 2 in Sine Magnitude. Next is r minus 1's complement. In base 10, r minus 1 would be 9's complement. In base 2 it would be 1's complement. You just change the r to whatever base you're using and fill in the number. Now this method, and actually all the other methods, use the same positive method of just taking the regular number and putting a 0 on its left. The question is just how you write down the negative numbers, how you define them. So in this case the positive remains the same, 0, 20, 20, and the negative number is the complement to the 9. You take each digit and you ask what number I need to add to it to get 9. So what number do you need to add to 0 to get 9? It would be 9. What number you add to 2? It's 7. And again, 0, 9, 2, 7, 0, 9. And you get your negative numbers. This conversion, of course, works the other way. 9, 0, 7, 2. You get the idea. Now, in binary, it would be about the same, just instead of 9, you have 1s. And it's very simple in concept because you just flip the digit. If you see a 1, you switch it to 0. If you see a 0, you switch it to 1. You just flip all the digits and you get your negative number, or your opposite signed number, because you could start with a negative number and go to positive. It's the same way of conversion. In mathematical terms, you could just write a series of the r minus 1 and subtract the 2. So you write as many 9s as your number's length, and you subtract the two numbers and you get this result. Same with binary, you just write 1s, you subtract, and you get this result. Now, I didn't talk about addition and subtraction. If you think about it, it's not very different from what you know from first grade or second grade. You just need to think with different digits in mind, but it's the same thing. Now, r's complement, which in base 10 would be 10's complement, in base 2 it would be 2's complement. Our positive numbers are exactly the same, 0, 20, 20. But what we do now is that we write down a 1 on one digit left of our number and a lot of zeros, and then we subtract, and what we get is the new number with the negative sign, which is 97980, because if you subtract these two numbers you get this result. Now this doesn't say much, so another method of going is just taking the r minus 1 complement, and you do it the same way we did in the previous slide. You get 97979 and you add 1 to it, because r's complement, it's like r minus 1 plus 1, and you get the exact same result, and it works in every base. Same in binary. Binary, you again could do the 1 and zeros and subtract, or you could just flip all the bits, all the digits, and add 1 to it. So if you flip it, you get 1000, you add 1, and you get 1001. Another method of doing a tools complement in binary, and binary only, because I don't know if it applies to other bases in some capacity. What you do is that you take your number that you want to convert, and you copy all the zeros starting from the right. You copy them down. You copy the first one you see. So here we copied the 1, and then you flip everything after that. So we copy the 1 down here, and then we flipped 1 to 0, 1 to 0, 0 to 1, and we're done. And that's basically how you do bases in the most basic way.